はい、皆さんお待たせいたしました。続きましてはですね、セッションといたしまして、アーノルドのですね、実際ソフトウェアエンジニアをされております、オートデスクから、お呼びいたしました、アドリアン・エルベルさんにお願いしたいと思います。よろしくお願いします。
Hi, I'm Adrian from Autodesk. I am working on the Arnold renderer, and I'm the lead programmer on the GPU project. Autodesk, if you don't know, it makes software for the architecture, engineering, construction, manufacturing, media, and entertainment industries. Arnold is a high-quality production renderer for visual effects in film and feature animation used by more than 300 studios worldwide, and this is some of the productions where Arnold is being used. Arnold was instrumental in the shift toward physically based light transport simulation in production rendering, a role recognized with an Academy Award in 2017. Arnold is available as a standalone renderer and as a plugin in Maya, Max, Houdini, Katana. This talk is divided in two parts. First, what we're trying to do with Arnold GPU, and then the more technical part, saying how we're trying to do it. So if you attended the Turing reveal at the NVIDIA keynote at SIGGRAPH, this image should be familiar. This is the result of our collaboration with Cinesight and NVIDIA. And we would like to thank all the people involved, getting the approvals, extracting the asset out of the Cinesight pipeline, tweaking it to work around the limitations of the engine, and removing some of those limitations, getting to work on the new hardware, on the new Turing hardware, was not a small feat. The result is a real production asset being rendered by Arnold GPU and taking advantage of the new Turing hardware. And in this case, it is a shot from the Avengers Infinity War movie, the character path, Spider-Man. So Arnold has been a CPU production path tracing renderer for the past 20 years now. So why did we start to work on a GPU version? The first reason is that we are seeing a shift towards more and more interactive workflows, like real-time look development or interactive lighting. And Arnold always had the concept of a render session where you can do live edits without reloading the scene. It's not just load, render. It's load, edit, tweak, change things, and then re-render. And the GPU brings the extra speed that is needed to make everything more responsive for those kind of workflows. Another reason for doing a GPU renderer is that all our users have been asking for it for the past 5 years, and we listen to our users. Which brings me to another reason. GPU now are getting bigger. Doing production rendering on a GPU 5 years or 10 years ago was very, very hard. But memory has always been an issue. But it is less and less true. With the recent Turing card, you can go to 48 gigabytes of VRAM, and you can pull those cards together. So the amount of resources available is now good enough for a lot of the productions. Other reasons is for small to medium facilities, it can be actually easier to scale using GPUs, because multi-socket CPUs are expensive and take room. You can put like 8 GPUs in a box. And GPUs are even available in the cloud now. So what were our goals when we set out to create Arnold GPU? So we wanted a single renderer that is feature compatible, pixel compatible, and API compatible. And I'll go into details on all those goals. So what does a single renderer means? It means the same settings, the same interface, the same nodes, the same binaries, the same code base. The only distinction is that small checkbox over there, where you can select CPU to GPU. The only thing we do as a user-facing feature is introducing the concept of a render device. And here you can see Arnold being switched from CPU rendering to GPU rendering on all the products we support: Cinema 4D, Katana, 3ds Max, and finally Maya on Houdini, of course. and finally Maya. So this is what we mean by a single renderer. Everything should look the same. Then we want to support everything. We want to support every Arnold feature. The goal is really to support all the shaders, all the lights, all the primitives, all the AOVs, everything. We don't want to create a preview renderer, we want a final frame renderer. Some features will be hard to support fully because Arnold is very flexible and customizable. So at first we decided to focus on character look development features first, but eventually everything will be supported. And here is a small showcase of scenes that were created by our beta users. Then the next goal is pixel compatibility. So we have this concept of levels of pixel compatibility. What do they mean? So the first level of pixel compatibility is you're an artist and you're doing look development, interactive lighting on your workstation using the GPU. If you kick the render to the render farm, you will get a result that is matching what you got on your local machine, a result that you can trust with the same settings. That is the first level of pixel compatibility between CPU and GPU, and that's already where we are right now. The next level of pixel compatibility is you're doing a production. And on this production, some shots are going to be rendered on GPU, some shots are going to be rendered on the CPU. And you can use those shots in the same production. The third level, which is harder, is you're rendering some images on the CPU and some images on the GPU for the same shot, and there's no flickering. You have perfect trust of your pixel compatibility. And finally, the holy grail, where we want to be in the next few years, is the same image. You're rendering some parts on the CPU and some parts on the GPU. And that's the hardest part to achieve. Of course, there will be some performance trade-offs. GPU are very good at hardware texturing, for example. Low-quality texturing will be extremely faster on the GPU, and maybe you want to take advantage of that. Some high-quality features are going to be hard to implement on GPU with the highest performance. So those are open problems for us right now. Maybe we will expose them to users, or maybe we will have a unified solution, but those are things that we are working on right now. Then the final goal, which is extremely important for you if you're integrating Arnold in a VFX pipeline or an animation pipeline, is API compatibility. Arnold is not just a standalone software. It is a ray tracing and rendering library, not a black box. This API has been part of Arnold's success, and as it made it easy to integrate in all DCCs and proprietary tools. And we designed the GPU acceleration as part of this API. So if you remember that checkbox in the plugins, that checkbox is really those two lines of code. This is a perfectly valid Arnold code. If you write that C++ code, you will get a render. And the GPU version is API compatible. So here is Arnold GPU being used on a medium complexity scene on a GV100. If you're familiar with Maya and Arnold, there is nothing new for you. Really, it's still that single checkbox. It's just that interactively, everything is a little bit faster. And you can see here, I am tweaking the sampling settings, switching the optics denoiser, doing rendering interactively. You can see that nothing is static, nothing is pre-computed. We can edit the scene without any problem. We can even live edit the geometry. Everything is still responsive. Of course, we also support lighting features, and interactive lighting is possible. And still in the spirit of real-time look development, or interactive look development, I should say, editing materials is also not a problem. Even the somewhat complex shading network that is on that robot. Oh, and here is the same asset in Arnold GPU directly inside the Maya viewport. And finally, you don't have to have a gigantic GV100 to use that tool. You can use that on your consumer hardware. This is on a GeForce 1080, and this was rendered by one of our beta users. The Arnold renderer and the optics denoiser working together. This is an interesting character, as everything, including the cloth, has subsurface scattering. So it looks easy, but it just only looks easy. It is kind of complicated. And of course, speaking of subsurface scattering, you know that rendering Lego bricks is complicated from if you zoom in, because the light will actually enter the Lego bricks, bounce around, and then exits. And everything, again, has subsurface scattering here. So this concludes the what we're trying to achieve part. So now let's jump into the how we're trying to achieve it. So first, Arnold GPU is using optics. And the optics framework has improved a lot over the past 2 years. And if you're like me 2 years ago, and the last experience you had with optics is the version 1 or version 2 or even version 3, take another look, because the improvements are real. We've been having a great collaboration with the optics team, and this collaboration has yielded lots of the amelioration in optics, including the motion blur specification. The just-in-time compilation is now in parallel and much faster. And recently, OSL in optics is beginning to be supported. So what we like about the optics programming model is, while it's quite rigid, it's also a compiler that can take quite a lot of complicated code and generate a good GPU renderer. And we all know the cost of flexibility. It is easy to write a fast fixed function renderer. It is harder to make a complicated feature with a lot of option efficient. And this is even more true in GPU rendering. Optics helps. And of course, and that's one of the most important things about optics, is that optics enables us to totally utilize the RT core in Turing hardware, something that we can now finally talk about. So there's many aspects to writing a production renderer. I'm not going to cover all of these because I would need the day to do that. But I'm going to focus on shading networks and how we leveraged optics to implement them on the GPU. So here is a typical shading network. That's the shading network on the robot I showed earlier. So there's around maybe 70 shading nodes here. I'm not expecting you to follow everything, but here roughly how it's divided. You have image nodes on the left, and artists love to pack lots of info on image nodes. Not just color, but many, many info. And you have here what we call the Uber shaders, the materials. And in between, you have a large collection of nodes that do color component shuffling, range editing, some procedural content creation like noise and flakes. And artists love to create those kind of shading networks because it enables them to do tons of small variations. And also, they want to be able to paint, to edit any of those parameters, to change connections all the time. Those shading graphs can be arbitrarily large. And they do support lots of small features like sub-component linking or different casting rules between parameters, like float to vector, vector to float, or color to closure, which is interesting to support. So how do we run this efficiently on the GPU? So remember I talked about API compatibility, and this is where it comes into play. This is a real Arnold shader code node in C++. This node will mix two lists of closure. And this code runs on CPU and on GPU without any modification. What we did is leverage the fact that Optix is a compiler, and we support the Arnold shading API on CPU and on GPU. And we plan to expose that to our users so that they can write their own shaders. You can write shaders, you can write cameras. So now that you can write a single node, how do you connect 70 of them together? So there's two approaches for that. You could inline all the codes of those nodes into a single program, like a single Optix closest hit program, for example. But the problem that with arbitrary shading networks, the amount of code generating would be gigantic. And every small modification of the shading network would result into a recompilation. And if we look at our compilation time, the just-in-time compilation time for our closest hit Optix program right now is already 45 seconds. So it would be at least 45 seconds every time you modify a node. So that's not practical. And it will also ruin the fact that Optix is now doing program caching. So then what we did is really the very simple approach. Again, we leverage the fact that Optix is a compiler. And what we do is we use Optix callable programs to implement every of those nodes. And we use a single Optix callable programs per shader. It is extremely easy to implement. And we were surprised about the performance because a large shading network evaluation will perform well enough. It will perform a bit worse than the inline version, but the flexibility it brings to the table is worth the cost. Not everything is perfect, obviously. For example, callable programs have overhead in code generation and runtime, and you can't trace trace in callable programs in Optix. Those limitations are work in progress. So, and talking about the overhead, so I took a simplified version of the shading network of this asset, and I inlined it by hand. And this is the overhead of the flexible engineering version. This is the render time of the inline version. And you can see that the overhead is again, good enough. It is there. It is definitely more expensive. But the overhead doesn't get crazy, and that's very interesting for us. Again, flexibility has a cost, but as long as this cost is linear in complexity, we can be fine with it. This is not the end of the story, of course. Maybe we could use an approach that is combining inlining and callable programs, like for example, inlining the smallest of the callable program together. Those would be fast to compile. Or really, maybe the end goal is to switch everything to OSL, because OSL by design will do this inlining, but in a very, very clever way. So this is something that we're going to work next. So this is really how we're implementing shading networks on the GPU right now. Then the second experiment I want to talk about is our experiments with Turing. And so we're only scratching the surface with Turing because we only had this hardware for I want to say 4 weeks now, really since 2 weeks before SIGGRAPH. So what Turing is doing is in Turing, the articles are doing acceleration structure and triangle intersection in hardware. So in theory, it is making ray tracing free. But the catch is in production rendering, the ray tracing part of the rendering is between 30 to 50% if you're lucky. So at best, you're looking at a 30% speed up. In practice, we're seeing much higher speed up to 2x on a GV100, which is the fastest and biggest GPU you can buy right now. And this is because Turing is freeing up some space to do shading by taking the intersection code and running that on the dedicated hardware. At least that is our explanation of it. But then, the scene rendering is now completely dominated by shading time. So this is something we need to work next. Another small experiment with Turing is, so Turing, the idea is ray tracing is free. We need to start casting more small and free shadow rays. So we tried increasing the shadow rays on the complex scene. This is on the Spider-Man scene. The Spider-Man scene has this tunnel of probably something like 20 quad lights. And so this graph shows the scaling from 200 million shadow rays to 5 billion shadow rays. This is the CPU. This is a GV100, and this is an RTX 6000. And you can see that on an RTX 6000, going from 200 million shadow rays to 5 billion shadow rays, the overhead is really, really, really small. And this is super interesting, because having access to those cheap rays may unlock new research. Before, we were doing lots of efforts into not casting any shadow ray, like including very, very complex sampling techniques. But maybe now this approach needs to be revisited. Maybe we need to look into approaches that are shooting a lot more rays, as long as those rays are cheap. And again, this is very, very recent work, and we're only scratching the surface here, but look forward to next research on those problems. And finally, where we are right now. So Arnold GPU is in private beta, and we are slowly ramping up the beta numbers. So if you're interested in joining, please get in touch at this address. And as usual, the official release date is when it's ready. And with that, I'm finished. Thank you for your time.